Hello, hello, getting the bits flowing. I had a pretty long stream yesterday, and this one's getting started later than usual, and I might have other stuff to do pretty soon, so this one might actually be kind of short, but had some stuff that I've been itching to share in continuation of yesterday's stream, so hopefully this will be kind of interesting, even if it's short. This is continuing on just a little mini project that was kind of utilitarian, where I needed to modify this USB switch that I usually use in my streaming infrastructure so that I can switch it between channels without kind of fussing with this hard-to-use button quite so much. So just doing my usual checks. Let's see if we're streaming. Looks like we are live on YouTube. We are live on Twitch. How's everybody doing this Friday? Oh, the cat camera is not even turned on right now. Anyway, let's make sure everything else is working. Hey there, Winchies. Oh no, Grumpy, I'm sorry. Fly in my face all of a sudden. Okay, yes, and we are live on Diode Zone, bugs and all. Thanks, bugs. Cool. Gosh, where did that come from? I hadn't seen any flies in ages. It was just like waiting for me at my streaming desk. So, I'm not gonna bother setting up the cap cam right at the moment because Tuco isn't around, but let's keep that handy just in case we need it. I was actually gonna format this card. Yeah, good evening everyone. How are y'all doing? It's funny, I used to think it was really weird that my folks would say y'all all the time, but now I find myself doing it more often. Alright. Got some cute little buttons here. These are actually very old. I remember buying them from a bargain bin at a electronics surplus shop back in Denver, Colorado, many, many years ago. But they're interesting. They're kind of tall. They don't have any kind of tactile click, which some people might find frustrating, but I actually find this sort of continuously springy feel pretty satisfying. And this might be nice for switching channels during a live stream because it doesn't make much noise, whereas this one, it actually doesn't make as much noise now that I have it outside the enclosure, but it has a big clacky tactile switch. You see that? You might also notice why I get frustrated by this a lot. If I'm, for example, trying to switch it from channel 1 to channel 4, I might like click it like 3 times or something. But if I just like click it 3 times, it might go 3 times, it might go 2, it might go 1. The button debouncing on this is very unreliable. So yeah, this has been a very frustrating user interface, even though the actual USB switch part of it works fine. So I just opened it up kind of on a whim on the last stream to see if we could improve it. The other reason to do this now, you know, because like there's plenty of projects, like why do this now? I was just rearranging some of the stuff on this part of the shop, and I kind of made the problem of the USB wiring being further from the user interface part to the desk kind of worse. So for this to work at all now, I'm running USB extension cords all over the place, much more than I would normally prefer to. So it would be great if I could both make the user interface for this less frustrating and make it remote so that I can actually have the user interface be separate from the USB switcher. So that's really what I want to do, is I want to modify this so that I can have a separate little user interface box, which is maybe something that's tiny and I can just like stick right above my keyboard. And then I can just press these buttons and go directly to the channel that I want and maybe even see which channel I'm on here. So that would be cool. And there are a lot of ways to do that. you know, I mean, like the simplest thing to do would be to just keep using a pile of USB extension cords, because that works, and then just keep this box as my user interface, but fix the firmware so that the debouncing doesn't suck so much, and I can use multiple buttons maybe. So that would be one option. This switcher has a feature I'm not using where it tries to automatically switch to a channel when that channel is plugged in by detecting the USB 5 volts. And I don't actually want that feature. So if I want to sacrifice that feature, that saves me 4 GPIOs that I can use for whatever I want. So that would be an easy way to add 4 buttons. And in fact, I don't think the stock firmware would quite do what I want if I just like use it as is and add buttons and treat those buttons as like voltage detect inputs, but it would be close. So like that would be one approach, is, you know, keep the existing firmware mostly unmodified and just treat the new user interface as voltage detect inputs. But I think I want to do something slightly nicer and have a actually remote user interface. Could do that just by running a bunch of separate wires for each button, or by using a pretty heavy cable. But I also wanted to use a pretty small wire. Oh, is there no audio? That explanation's not going to be useful if the audio isn't recording. My OBS thinks I have audio on this end. Although I might be basically out of time soon anyway. Well, let me see if I can get through this little recap, because I've got some recap momentum to just kind of talk about where I'm at. And maybe instead of like a work stream, this will be more of just like an explanation stream, and we can do the actual work like tomorrow or whatever. So anyway, where was I? So yeah, I wanted to take this USB switcher that I've been using already for these streams to switch between several different computers. The way I'm using these channels is I have a couple of different workstations that I use for demos. There's one that I usually use for demos. There's one that I usually use for my own like editing and everything, but sometimes they cross purposes. And then there's one for sort of the chat monitoring tablet, and then there's one for sort of the chat monitoring tablet, and then one for the actual streaming machine, which I need to use to like fuss with the OBS settings whenever. So at the end of last stream, we actually made a lot of progress and got to the point of pulling firmware off of this. It turns out there's just a standard STM, an STM8 debug interface enabled. You can read flash memory. There's no protection enabled or whatever. There were some enticing clues in the firmware. It looks like both the circuit board and the firmware have vestiges of infrared remote control support. So it seemed like, oh, maybe that's an existing serial interface. Maybe we just hook something up to the IR remote control interface, either an actual IR receiver or just use that as a serial input. But actually, depressingly, that seems to be vestigial from some copy pasta from what appears to be like a video switch firmware that they started with. And then, yeah, so the video switch firmware still has like strings and code left over from like HDMI and like YPBPR inputs and stuff like that. But if you actually trace through the code, which we did on the last stream, and we were tracing through the code just in a text editor, because I don't think there are a lot of tools that do STM8 disassembly. So we found just like a plain old disassembler and just did, old school reverse engineering in a text editor, and that was fine. And we traced through that IR code and found out where it was decoding the function, or decoding the individual commands on the remote to individual like functions in the software. But then it just did nothing with them. It was like a switch statement that had some debug code but nothing else. So it was vestiges of some infrared remote processing, but nothing actually useful. So that's kind of a dead end. Kind of a similar story with the serial port. We found a bunch of debug printfs, but the actual printf function was an empty stub. And nothing actually touched the UART except for some code which seemed to just turn it off, and then nothing was calling that function. So yeah, just some vestigial code, but nothing really useful. And the code that was there was not good. It's just like a bunch of kind of copy-pasted stuff that seemed like they just did the minimum amount of work necessary to make it work, which is not surprising. But just means that there's not a lot there that's really worth building on, probably. So yeah, at the end of the last stream, we had that kind of figured out and got to the point of writing sort of a hello world firmware for this board, which could just cycle through the inputs. And so, like right now, it's back to running the original firmware. I just loaded the original firmware on here just so that I could use it again. But if I flash the firmware that we've got here, so this is flashing the current work in progress firmware. And it just went, it went kind of all the LEDs on for a moment as it was reflashing. But now it's running through a proof of concept firmware that actually just cycles the switcher slowly. And the LED actually matches the channel that it's set to. So we verified that on the last stream. So we've got basically like a scaffold for a USB switcher now. There's a function we can call in C. The compiler's not great. This is SDCC because there's no like GCC or LLVM port for this processor. So it's, you know, the compiler is a little restrictive. SDCC is like basically the worst C compiler that I'll still tolerate using. It's not great, but it gets the job done. It's like, it means I don't have to learn a new assembly language just to make this project happen. So, so yeah, I've got this little scaffold. So at this point, actually, I'm going to switch my user input back to a hardwired connection that bypasses the switch, because otherwise it's going to be cycling me. So I'm going to connect my keyboard directly to the demo machine now and bypass the switch. We don't need this window open, that's just confusing. So yeah, this is the firmware so far. It's written in plain C without any libraries, so it's just pinging on GPIO registers directly. Somebody might have header files for STM8, but I haven't looked for open source ones. So I couldn't even find the document that listed the base addresses for all the GPIOs, which, you know, and then of course I was doing this like when I was already tired at the end of a stream and like couldn't multiply and divide, so I was calculating the wrong addresses in my head for all the GPIO registers. Lost some time on that, and that was kind of frustrating. But now we have the right GPIO defines. These are still kind of hard-coded, but we at least have some functions that you can call to set the active channels, and all of this actually works. There's just a little kind of awful hard-coded delay loop, and then we cycle the channels, and that's all great. So at the end of the last stream, I was planning on adding serial input to this, thinking that maybe you just have like 3.3 volt or 5 volt serial that's like 9600 baud, or even like 300 baud or something just for signal integrity, and maybe you just send in an ASCII character to switch channels. But thinking about what I wanted on the other end of that, kind of between then and now, I don't know that I really want to put like an entire microcontroller on the other side. Like I could make my own little board with, you know, a little 8-pin AVR, and that would be pretty small and economical. I could use a trinket, which is kind of the next best thing without having to design a custom board for that. But the trinket, I mean, basically using an 8-pin chip doesn't really leave you enough I/O. You basically still have to use some kind of Charlie plexing trick to get a lot of your I/Os back. So that starts to become a little less appealing. You could use a micro with more pins. So I could just use like a, you know, I have like some SO package and DIP package AVRs we could use. That just starts getting more complicated, where like I just wanted this to be like a really quick project. I didn't want to be like designing a separate circuit board and writing 2 firmwares. And so I started thinking it would be really appealing if I could do this without a separate microcontroller, just by modifying the firmware on this and maybe doing a very simple hardware mod. So then I was thinking, well, what could I do with a small cable, something that's still convenient? So it'd be really nice if I could run this on an 1/8" like headphone style audio cable. So 3 wires. I don't necessarily have to use them as ground and 2 signals. I could just use them as 3 wires. So that got me thinking about what I could do with Charlie plexing. So yeah, I'm a little rushed for time, so I won't draw like a new diagram for this maybe, but I drew this like tiny sticky note diagram on this. I was thinking about Charlie plexing as a matrix. There are a lot of ways to think about this, but one way you can think about this is that it's like an LED matrix. It's like any other matrix of like driving LEDs or scanning switches, where you have, you know, maybe one set of signals for rows, one set of signals for columns, and then at the intersections you have an LED or a switch or something, and then you set one row and then read all the columns, you set the next row, read all the columns, etc. There are a lot of variants of this matrix scanning approach. Charlie plexing is the realization that the rows and the columns can be the same pins, basically. I mean, there are a lot of ways to think about Charlie plexing, but that's kind of the way I like to think about it. And so you can imagine that it's like a matrix where the rows and the columns are actually physically the same wires. And the diagonal of that matrix represents all the combinations where you would have the same wire, so there's no way to have a current loop. But everything that's off the diagonal, every square off the diagonal in that matrix represents a potential current path through that set of wires. So if you have 3 wires, then you have 6 potential current paths. So traditionally, Charlie plexing with LEDs, that would give you 6 LEDs by wiring an LED in each of those different combinations indicated by that diagram. You could add switches into that by having switches in combination, like a momentary switch in series with an LED in place of, a momentary switch in series with a diode in place of that LED. So like one way to think about this is we have 6 potential current paths, and we can mix and match those between like LEDs or switches or other circuits. But that's still not enough, because if I want 4 channels, an indication of what channel is current, I need 8 things. Like I need 4 LEDs and 4 momentary switches. There's some other things I considered, like what if you have LEDs where those same current paths are also used as switches, and you use a normally closed switch in series with the LED, and so you can treat that as a diode and just like scan that like it's a keyboard matrix, or light it like it's an LED. But then when you press it, while you're pressing it, you're kind of breaking that circuit. You might know, yeah, it reminds me of some, well, the effect would be a little bit like kind of an old school doorbell, where like in those cases, I think when you press the doorbell, they were wired with like a switch and a light bulb in parallel. And so pressing it would short out the light bulb and the light would go out. And this would be similar. Pressing it would disconnect the LED and the light would go out. So it would be a little weird from a UI perspective, where pushing the button, it would momentarily go out, and then when you let go, it would be lit. But I think we can manage that. The trouble with that is that it would require using momentary, normally closed switches, which exists. They're just not as common, and I can't just pick up any random like lighted switch out of my junk bin that I want to use for this project and use it. So my requirements here, if I want something that uses 3 wires, has 4 LEDs, 4 switches, and works with momentary, normally open switches, that starts to look a little weirder. And so I was like racking my brain about that this morning, trying to figure out what we could do. And I think I came up with a solution. I'm not totally sure it works, because I haven't tested this, but I have an idea. Oh, here it is. So it's like Charlie plexing, where you're dealing with the current paths that result from 3 wires. I'm using 4 of those current paths for LEDs, but then those other 2 current paths, which I'm selecting here using just whatever diode. I put in a 1 in 914 in the schematic because that was easy in KiCad, but it's probably just any diode that I pick out of my junk bin. I might use like a high power diode just because I have a bunch of those. So just whatever diode. So then it would be pretty straightforward here to just put 1 switch there, 1 switch there. Now you've got 4 LEDs and 2 switches, but I want 2 more switches. So I had this idea to, at this point you could imagine using all sorts of other sort of like analog properties of this. You could make voltage dividers. You could, basically you could think of gradations in voltage, current, or time as ways to solve this problem. And this is sort of just an analog, low-tech way, to do a serial port almost. It's like a way of having a time-varying signal that conveys information. It's just we need very few different kinds of packets in this setup. So my thought here is 1 diode, but maybe 2 different switches. 1 acts like a short circuit. 1 starts out acting like a short circuit, and then this capacitor charges up, and it starts acting like a voltage source. So the way you would scan this is you would first of all, the way you would scan a normal like button matrix with diodes is you would tri-state the pins you're not using, and then set this to low and you'd set this to a weak pull-up, which this microcontroller does have built in. It has like, I think they're like 80 or 100K resistors on the pull-up. So without any additional hardware, we can just encode, tell this pin to be connected to power supply through a 100K resistor, while we can simultaneously read it as an input. And then we can tell this side to be ground. So you would do this, scan through all the possibilities, and notice which ones you read back as high and which ones you read back as low. And because this switch would, when you press it, cause a current path that allows this diode to, you can think of the diode as sort of like, if it's a voltage divider, it's sort of like vastly overpowering that 100K resistor, you know. But you could also imagine it as, you know, if you're kind of stacking voltage potentials, you can imagine, well, this is near ground, just as close as the, you know, the low side driver on your microcontroller can get it to ground. This is one diode voltage drop above ground, so like, you know, 0.6 volts or whatever you're dealing with. And then this node here is effectively the same potential that the input side of the port is at. So, and then you can imagine that 100K resistor is kind of acting like a weak spring, kind of pulling it up to positive voltage. But this is, you know, this is kind of clamping that voltage down to ground and not allowing it to raise any higher than the voltage drop of that diode. So we'd be able to read that as a 0, whereas if the switch was up, you know, if you're not pressing the button, then there's no current path here, and the weak pull-up will, it almost kind of helps, I think, to think about that parasitic capacitance in the GPIO pin as requiring, you know, current to charge up, which is actually what's happening. I find that to be useful for imagining these kinds of circuits. So when you turn on that weak pull-up at that instant, you're now charging up that capacitance in the parasitic, you know, capacitance of that I/O pin, and very quickly it will become high. Not immediately, but probably quickly enough that we don't need any additional delay. So that's like what I would expect from a weak pull-up on this side, ground on that side, on one of these regular pins. But then I'm thinking, well, like, what if we add some capacitance into the system? So now, what if we try to time how long it takes to charge this capacitor? So I'm imagining the way this could work is, and I don't actually want to charge it through the weak pull-up, I think. I think I want to charge it through a resistance that's a bit more tightly controlled. So on the other side of this, on the other side of the audio cable, I actually have these 220 ohm resistors, which are the same resistors that you'd want for current limiting on the LEDs or thereabouts. We might want to adjust these up maybe, but that was where I was starting. So the same resistors that we would use for current limiting on the LEDs also current limit the process of charging this capacitor in a somewhat more reliable way than just using the weak pull-ups. So maybe you divide the scanning into 2 phases, like a charge and a discharge, and then you maybe loop that to see how many charge cycles it takes to change the value from a 0 to a 1. Or sorry, not charge and discharge, charge and measure. The thing about this diode is that you can't really discharge through the GPIO pin, so this resistor just kind of constantly discharges it. I was trying to hit a time scale of maybe like many milliseconds here and a fraction of a millisecond for the charge. So yeah, I don't know, it's kind of a weird scheme, and I'm going to have to save the proof of this for the next stream because I've got to wrap this up. But just kind of wanted to share what I was thinking here. What I like about this is that we could design a very simple, just passive component circuit that's easy to mount just wherever with 4 buttons, 4 LEDs, and then just wire that into the original microcontroller, write some new firmware, and that's all. We don't need a separate micro. We don't have to, you know, add another like $30 worth of components to the project. We can just do it basically for free. So that might be nice. All right, well, I think that's basically where I'm going to wrap this up for now. Keep it short and sweet. This is like the first time I've done a stream that was under an hour in ages, but that's basically where we're at. I haven't actually posted this code yet. I'm going to put this up on GitHub at some point. I don't, as a policy, share firmware that I rip off of commercial devices for copyright reasons, so I won't be sharing the original firmware. But I will share this one that's been written from scratch, just based on like looking at the port numbers and stuff. So we should be able to do whatever we want with this. If you want to just look at it on screen, it's here, but you know, if you want it that much, please don't type it in. Please just like send me a DM and I'll give you the file, but I'll put this on GitHub soon. All right, I'll see everyone next time. Just keeping it short and sweet. Thanks everyone who supports the channel by sending in objects and donating to the Patreon. The Patreon is what helps me swing the full-time video production thing that I'm doing here. So if you like that, the best thing you can do to help keep it going is to just chuck in $1 or $2 a month. But I also really appreciate folks who, you know, share my videos with other people, folks who I really appreciate folks who share what they like or what they don't like about what they're seeing here with me, because I think one of the things that I find most challenging on an ongoing basis is prioritizing what I'm doing and figuring out what to focus on. So yeah, I appreciate feedback, and I really appreciate all of you folks who have been supporting the channel for a long time. So thanks so much, and I'll just keep busy at the editing and the shop tidying and the streaming, and I'll see you all next time. See you later. Happy hacking.